We pretty much all trust AI search to find anything we throw at it. But what if there's a fundamental wall, one that's built right into its very design? A wall that even the smartest, most powerful AI can't seem to get over. Well, a recent discovery from Google DeepMind shows us exactly where that wall is.
So, let's start with a big what if. What if AI's incredible ability to understand what we mean, not just the words we type, has a hidden mathematical flaw? What if its single greatest strength is also the source of a massive blind spot?
All right, here's how we're going to break this all down. First, we'll get into AI's search superpower. Then, we're going to uncover this hidden mathematical wall it keeps slamming into. We'll look at the unwinnable test researchers built to prove it, figure out why these amazing models are failing, and finally, check out what's next.
So, first things first, let's just take a moment to appreciate what makes modern AI search so incredibly powerful. I mean, we've come a long way from just matching keywords. The big leap is from that old, rigid keyword matching to what we call semantic search. You know, back in the day, if you searched for fast car brands, you'd only find pages with those exact words. But today, a semantic AI knows you're also probably interested in quick automobiles. It's the difference between just reading words and actually understanding concepts. Now, the magic behind this whole thing is called vector embedding. It sounds complicated, but the idea is pretty cool. The AI basically translates any piece of text, a word, a sentence, whatever, into a long string of numbers, called a vector. You can think of it like a coordinate on a giant map of meaning. So similar ideas like fast and quick end up as neighbors on this map. That's how an AI gets the context. But this is where the plot thickens. This amazing technology, this giant map of meaning, well, it's not infinite. It's got a hidden wall.
And that leads to a really critical question. Is there a limit to what these number strings, these vectors, can actually represent? The researchers dug in, and the answer they found was a huge, resounding yes.
Okay, here is the best way to get your head around this. Think of an AI's embedding dimension. That's just the length of its string of numbers, like a painter's palette. If you've got a fixed set of colors, you can paint a ton of different pictures, right? But you can't paint every possible picture. You are fundamentally limited by the colors on your palette.
And look, this isn't just a nice metaphor, it's a mathematical certainty. The folks at Google DeepMind proved that for any given AI search model, there are combinations of documents that it is physically incapable of returning to you. It doesn't matter what you ask or how you phrase it, some answers are just off the map. But this wasn't just a theory they cooked up. To prove it, the researchers designed a deviously simple test. It's called Limit, and it was built for one reason: to find this hidden wall and watch the AI run smack into it. You're going to laugh at how simple the limit test is. It's built on just basic facts, like John likes quokkas. Then, these facts get combined into simple documents. And finally, the AI gets asked a really straightforward question, like who likes quokkas and apples? The answer is right there in the text. I mean, this should be a piece of cake for a modern AI, right?
Well, the results were staggering. And we're not talking about just any old models here. These are state-of-the-art systems like GritLM and Gemini. And on this incredibly simple test, they completely fell apart. I mean, their scores barely scraped into the double digits. It was a spectacular failure.
Let's just be crystal clear on this. The world's best AI search model scored less than 20% on a test that a kid could pass without even trying. They couldn't reliably find one person who liked two simple things. This wasn't just a little bug, it was a total, fundamental breakdown.
So, what on earth is going on here? How are these unbelievably powerful and complex models failing such a basic task? Well, the reason is actually way deeper than you might think.
Now, the first logical thought you might have is, well, okay, maybe this is just some weird new kind of problem the AI hasn't been trained for. And that's a totally fair question. The researchers thought of that too, and they tested for it.
And what they found is fascinating. When they trained a model on data that was similar to the test, its performance barely budged. The only way the model could pass was when it was trained on the exact test data itself. In other words, it just memorized the answers. This proves the problem isn't a lack of training, it's a fundamental lack of ability.
So the real culprit here is something called representational capacity. Remember our painter's palette? The limit test is like asking the painter to create paintings that use every single possible combination of colors. The number of combinations of who likes what grows exponentially, and the AI's fixed size vector, its fixed palette, it just gets completely overwhelmed. It literally doesn't have enough colors to represent every possibility.
The researchers even came up with a metric for this, which they call connection density. You can think of it as how tangled up the information is. For standard AI tests, that density is basically 0. But for the limit test, by design, it's thousands of times higher. It's that exponential explosion of connections that just breaks the single vector model.
So, if the dominant model we're all using has this major flaw, where do we go from here? The great thing is, this research doesn't just point out a problem, it actually points us toward the solutions.
And there's some really promising ways forward. Turns out, older methods called sparse models, like one called BM25, scored around 93%. Why? Because they use these massive high-dimensional vectors, giving them a much bigger painter's palette. Other new approaches, like using multiple vectors for each document or these powerful cross-encoders, also solve the problem, with some even hitting 100% accuracy.
So, here's the big takeaway from all this. The single vector model, which is the workhorse of modern AI search, has a serious, fundamental blind spot. It's powerful for sure, but it is not a one-size-fits-all solution. This discovery is basically forcing the entire field to think differently and build AI that can handle not just concepts, but the messy, complex combinations that make up our actual world. And that really leaves us all with a huge question to think about. As we race to build these ever more powerful AIs, are we paying enough attention to their fundamental limits? Or are we building these incredible, towering structures on a foundation that might have some hidden cracks? It's a question we all need to keep asking. Thanks for joining this explainer.